Hello and welcome to part 2 of our 7-1 lesson. Today is going to be, so we call this part 2, it's going to be instead of ratios and proportions review, it's going to be radical review. So radical review, and we're predominantly going to be focusing on how to add, subtract, multiply, and divide with radicals and then simplifying those radicals. So in the next, pretty much for the rest of the year, we're going to see radicals relatively frequently. So it's important we know how to use these basic operations with them and how to simplify them properly. So let's start with simplifying radicals. Simplifying radicals. Okay. If we ever needed to simplify a radical, for instance, the square root of 18, this could be simplified a number of different ways. For instance, so let's call this example 1. For simplifying radicals, we could do this method, let's call this method 1. We take the square root of 18 and we focus in on numbers that are perfect squares, or that have that are perfect squares. So for instance, 1 squared is 1, 2 squared is 4, we keep going, 9, 16, 25, 36, 49, 64, 81, and 100, okay? And the idea is all of these numbers can be square rooted, right? So what we want to do is we want to look for one of these numbers that divide perfectly into our radical. And in this case, 9 is the perfect square that we want to use. So we break this up, we take the square root of 9, and the product of 9 and what make 18? Well, 2. 9 times 2 is 18. And from here, we could actually take the square root of 9. So we take 3, the square root of 9 is 3, and we include the 2, the square root of 2. Square root of 2 is as far as you could go with that. It's a prime number, and that's as far as we go. So that's method 1, where we use perfect squares. So if you want to put perfect squares, then that's that method. Method 2 is a little bit more universal. Because if you don't know your perfect squares well, then I would recommend this method. What you would do is you do some prime factorization. If you recall this from maybe 3rd, 4th, or 5th grade, prime factorization is when you start making a factor tree in which all of the factors are prime. So if you want to look at this as, for instance, root 6 times the root 2, you absolutely could. Root 2 is a prime number, so I'm going to highlight that. And then 6 can still be broken up. We could break this up into wow, this is not right. Hopefully someone caught that. 6 times 3 is 18. So 3 is a prime still. And then we break up 6 because 6 still has factors. We could say root 2 and root 3. Root 3 is also, these are both prime numbers. And if you notice, we actually have two of the same value, or 2 of the same radical. And when you have the same radical, they're paired off, same radical pair. Well, root 3 times root 3 is root 9, and we know the root 9 is 3. So ironically enough, when you pair these, it just becomes, you pretty much just take that value, 3, okay? Because squares and square roots, this pretty much is what it looks like. 3 times 3 is 3 squared, and there's a square root there. Squares and square roots cancel each other out, and you're just left with 3. Now, nothing happens with the root of 2, so we just kind of tack that on at the end. And if you notice, we get the exact same answer. So either way you do this, whether it's prime factorization or perfect squares, prime factorization, they're both good methods, okay? So that is your simplifying radicals. Adding radicals is slightly different. Adding radicals, for instance, if we have, let's call this example 2, if we have 2 root 3 plus 5 root 3 minus 3 root 5, okay? Now, if you recall this from Algebra 1, you kind of treat these like terms, like terms. For instance, if we rewrote this problem, 2x plus 5x minus 3y, these are two different terms, x and y. Very similarly, the root 3 and root 5 are two completely different terms, okay? So you cannot add these together. However, just like here, on the right side, you could combine 2x and 5x because they are like terms. 2x and 5x make 7x. And that's actually what we do with these values. We add the coefficients, 2 plus 5, which is 7, and root 3 should stay the same. We can't do anything with the last term because it's not the same radical, so we leave this as minus 3 root 5, okay? So, if you want to finish this one out, this would be minus 3y, and then there's the same idea, same concept, okay? So that's how you add radicals. Multiplying radicals is arguably the easiest. Multiplying radicals. When you multiply radicals, you literally just multiply the terms. So for instance, example 3. If you have, let's say, x, oops, not x, 2 root 3 multiplied with 3 root 6, okay? All you would do is multiply the proper terms together. So for instance, 2 and 3 are the coefficients, and then root 3, root 6 are the radicals, and you multiply them accordingly. 2 times 3 is 6, and then the radicals, 3 times 6 is 18, and that stays inside of the roots. But if you remember from up above, we were able to simplify the root of 18, and we've actually already done that here, right? We know it's going to be 3 root 2. So what you do here is you simplify this, you break this up, root 9, root 2, the 6 drops down. We know that the root 9 becomes 3, root 2 still drops down, and the 6 also drops down, but we also have to make sure we are multiplying here. So 6 times 3 ultimately becomes 18, because now these are both on the outside of the radical, they multiply together, and then root 2 just drops down. So this is our final answer, 18 root 3. So make sure you're just multiplying the proper terms together, the coefficients multiply, and then the radicals multiply, okay? Last thing we do is division. So dividing with radicals. And this is a little bit tricky, okay? So, for instance, if we have, let's call this example 4. If we have, let's go 2 root 5 minus 3 root 3 over, actually let's change this. Let's make this a 4. And maybe not a 4. Let's make this a 6. And then on the denominator, let's do 3 root 5. Okay. A couple things happen here. One, we have to distribute this as if it's like a grouping division. Okay. So what we do is take the I personally would separate this, right? I would take this as one fraction, and then I would take this as another. So I'll show you in color. I'm going to separate this by saying 6 root 5 over 3 root 5 minus, and then in red, 3 root 3 over 3 root 5. Okay? So I split up the denominator and made it the denominator in two different fractions. And when you do this, you could simplify it accordingly. Well, we could actually do this. 6 divided by 3 is 2. And root 5 divided by root 5 just cancels each other out. So that's actually really, really nice. Over on the right side, we still have the minus here. 3 divided by 3 cancels each other out, which is nice. But this does not quite work out, so we actually have to do a fancy trick. You're not allowed to have denominators or radicals in the denominators, so the way you fix that is you just multiply the numerator and the denominator with whatever's in the denominator. So for instance, this is root 5 on the bottom, or in the denominator, we multiply root 5 over root 5. The reason why we do this is because, well, 5 times 5 is 25. What's the square root of 25? That's equal to 5. That goes along with, once again, pairing radicals of the same value. And we have a value of 5 in your denominator. In your numerator, we just take 3 times 5, which is equal to 15. That stays in the radical, or in the numerator, as a radical. And our final answer will become 2 minus root 15 over 5. Okay? With that said, we'll do some in-class practice, and then I'll see you in the next one. Bye.